So there's two related talks. The first one is the one that I'm going to make, and then the second one will be the one of Richard Foster that is following me, about the collaboration spotting tool that we are developing as a project at CERN. So I will present you the main lines of the project, some mathematical background for the visualization, and if you have, and I will speak of the challenges that we have to solve to have a good visualization, and then we will go for the questions. So, collaboration spotting project has started maybe 4 years ago, I think, and it has been the current framework has been developed by Adam Agox and other people, Jean-Marie Medegoff, and some other people that were coming before. That were in the project before. We have different applications that are already functioning. One was with JSC, that was the beginning of the project, and it's currently running at teamanalytics.io. It's a transform project, but now we are also doing other applications, some with the Wigner Institute. So the idea behind is to allow visualization of non-numerical data and to try to make links in the data sets and to visualize them properly. So we try to follow the framework proposed by Sasha and his collaborators, and in this framework, the idea is to from the data we are pre-processing the data, so building collaborations, making the search of communities in the collaborations that we are building, then we transform it to have a proper visualization. And at each step, we would like to have a feedback, and that is given so we can have better experience in visualization. So that's the well-known views of big data. I go for. So what we want is to build the links for the data, and data are stored usually with metadata attached to it, and from this metadata, some are of interest for analysis, like title, abstraction, citations, and some are interested for visualization, like organization, cities, keywords in publication and patents. That was the first use case. In collaboration spotting, we want to visualize the multidimensional network structure and interconnectivity from different user-defined perspectives. So for this, we have to compute collaborations and visualize these collaborations in a way that we have the maximum cognitive perception. And this, for small graph, it's quite easy, but when we start to increase the number of collaborations, then it starts to be quite hard to have a good cognitive perception. So my role in the project is to work on this visualization part. So to achieve this, we have to learn the intersect network structure. So we try to separate whatever is separating. So try to find the connected components. We can measure node degree distribution. We can customize and adding communities. But very often, when the number of dimensions is increasing, it's hard to combine the different dimensions, and you have to have a proper modeling of the networks you have behind through hypergraphs that allows you to travel in between the different dimensions. The learning with hypergraphs, so we have to specialize algorithms to take into account those hypergraphs. So that's is under processing at the moment. And we have also, when we are building communities, we have to label those communities. So we have to make a semantic abstraction. So that's another way to simplify the visualization at the end. And this is a full PhD that is done by an Austrian student. So what is an hypergraph? An hypergraph is just a generalization of the notion of graph. So instead of linking two vertices, we are linking end vertices. And so instead of speaking of edges, we are speaking of hyperedges. So the great advantage is that we have the set approach, but also the graph approach. So there's a dual view of this in this case. So to build an hypergraph from the metadata, what we are doing is that we take a physical reference. For instance, a publication is a reference, and then we are building a collaboration for it. So each organization that is cited in one publication will make a collaboration. So as some experiments at CERN can have articles with 450 names and organizations, that makes huge collaborations. Then we have to build the reachability graph, so what we can reach from one dimension to the other, so the dimensions that are cited in the same publication. So for instance, in a publication we will have organizations, but we will also have keywords. We will have countries, cities, and plenty of data that can so we can link them to the publication, and so we can navigate in between the different dimensions. I will show you how we can do it. So I explain you how to build the hypergraph. Just we take the nodes as the organization, for example, and building this hypergraph, it's just making a set of sets from the reference. And in this case, because each hyperedge is linked to the reference, then we can take another type, another dimension, and going from one to the other for the reference. And that makes the navigability. So to visualize hypergraphs, there's many solutions. One of them is the traditional set displaying, called as it's called Venn diagram, but we can also build the two sections of the hypergraph. That means that we will have click development of each hyperage. So in this case, we have something like this. So here we have 1, 2, 3, 4, 5 hyperages, and each time we are making clicks of the nodes inside the hyperages. So when you are making this with a graph, so this is a search on BGO crystals. It's the organizations that are working on BGO crystals. And so when you are making a search in the tool, we are going for this kind of graph. And that's the graphs that we are displaying at the moment in the version we are, in the former version. So another approach is the same. So each hyperage can be represented by a node. And so we make an extra node of it, and we link each node of the hyperages to this node. The great advantage is that we reduce quite a lot the number of edges. And so instead of representing clicks each time, we just have the number of edges that is equal to the number of nodes in the hyperage. And that leads to this kind of diagram. The great advantage is that you have less loss of information in it, because we can see the real collaborations. So if one collaboration is inside a set, a bigger set, we will see in this case that we wouldn't have seen it in the other case. So the possible gain is n factor of n minus 3 over 2. As soon as n is more than 3, we will gain. But there's an evaluation to make, because there's some unfavorable cases. And so this has been done, and we have shown that in our cases with the data, we have, most of the time we gain, and we gain a factor of 3 in edges. So that makes, that should make nice results. So the great advantage of the hypergraph approach, it's that it allows navigability. The visualization can be improved with the external view, and so the experimental evaluation that we have conducted allowed us to conclude that it was a good approach to visualize those kind of collaborations. And if you look at here, you have the big orange organizations, collaboration here, and here it seems just that we have a very big stuff, and when we see it just this way, we see that it's just maybe one shot, and maybe there's one or two other collaborations, but this net was much more important in the ways they were more collaborating. And so we have hidden information on the left that are displayed on the right. So the remaining problems is how to visualize a large graphs with maximal knowledge and discovery nice layouts in a time acceptable for the user, because it's a web application, so we can't wait for ages to show the graph we have to compute. So there's a few principles for aesthetics of graphs. That's known as Gestalt principles of groupings. So that's it leads to the aesthetics that I will show you after. If we are using those different Gestalt principles, it will help to have better visualization. And so we can make a link between those Gestalt principles and what we can do in graph to improve those principles. And there's also some graph drawing aesthetics, and that I have regrouped by kind. So more or less, what are we doing? So we are making a search, we are building collaborations, we are building the hypergraph corresponding to it. We build the graph. So at the moment, this page it is here, but I think at the end we will put it here when we will have adapted all the algorithms to have a proper HPHS support. And so after we made clusterization, layout, building, inventory. And so the computationally demanding phase is in red. And of course, all our attention is focused on this part. So for this part, we are doing quite several stages. First stage, finding connected components, then building the connected component graph. So the graph made by where the nodes are the connected components. We made a sorting of the connected components by the number of reference it has behind. So at the final layout, I will show you, we will have an ordering, so it will help in the knowledge discovery. Then we are clusterizing each component, building the question graph for each connected component, and we also compute the connected components layout separately. And at this stage, if the number of nodes and number of edges is under a certain limit, we just display. Otherwise, we have to recalculate for the question graph and going to try to summarize. So we just do one loop at the moment, but we might do it several times. And then after, the problem is to labelize the communities. So some facts about, at the beginning when I arrived in the project, it was only force-directed algorithms that were used, and so it was quite slow. And also the main problem of it is that it's shown that it's not scalable because we arrive in a lot of local minima, and this is a huge problem. And so we may not have the best layouts we can. So circular layout, I have tried some with images. It's quite, we can have some good information in it that we can do better. So with circular layout, I'm making level, so here it's an average. And so I have sorted by cluster. I didn't calculate the connected components on this one because it's a node snapshot. And we are organizing the cluster and we just organizing them by the number of connections they have with other clusters. So the more they are centered, the more they have connection with the others. And I just put the extra node of interconnected cluster inside. When we have an average that is working with another average, then I put it in the center. And here, just the white are the extra nodes to make them clickable. Another approach was to separate connected components, trying to, so we don't see much, I can hardly, I thought it would be better. It's a bit so. So here just we have organized, so we separated all the non-connected communities were put on a circular base outside, and all the interconnected communities were put in gray. The edges were put in gray and were put inside. If we use the quotient graph, we can have these kind of things. So I'm going quite fast because I have no more time. And so, if we take an approach by connected components, I've just implemented it. It's not yet in the publication and patterns use case, so I don't have snapshots, but it will be something like this. So here I have one connected component, which is here, where I have made the clusterizing. And then I have other connected components that are around, and they are organized so that we have the number of references that are decreasing along the side. So each round will decrease. So the most important thing is inside. You have the same graph with the approach of communities. So I just lower down the threshold for the edges max and nodes max. So of course here it's a community 0, 0, 1 and so on. So the labelization has to be made afterward. What was? Oh yeah. Also, filtering with hypergraph is quite easy because we just have to withdraw whatever we want, and we can see only the connections and the organization that are essential to make the connection in between different collaborations. And the idea is to have a very full cube of data with different dimensions. So here the organization, here the keywords, and having interaction between the different facets. So this more or less have talked about. Thank you for your attention.
Thank you very much for the talk. We have time for 1 or 2 short questions, so please.
So I'm curious, so part of it is a visual thing, right? Isn't that subjective? Like actually, do you try the Apple approach, like try to find something which works for everyone and that's it? Or is it more like that there are parameters and everybody tries to define what they like, how they want to see the graphs? Which approach do you try?
So at the moment, it's more or less, we try to summarize as much the things as we can. And then the other step will be, so what we try to have is a modular approach. So after the user can define his own algorithms when it will be needed. So at the moment, yeah, it's just one way, but we will propose different layouts maybe at the beginning, and then after, because it's modular enough, then because clusterization algorithms has to be defined by the domain where we are making it. There's plenty of things that has to be parameterized. So the principle is to navigate in between dimensions. And then after, we can customize. And we try to make it as generic as possible, but also as customizable as possible.
Okay, any more questions? Okay, then maybe in the coffee break. So thanks, that's
okay. And I can maybe at the break at lunchtime I can show more of the tool, unless Richard maybe makes it. Do you show the tool? Oh, okay. So maybe we can make a demo of the tool directly connecting to the.
Okay, that's fine. So in the coffee break you can watch a demo. Okay, so thanks to the speaker again.